Hi, this is Anthony Hanani. Hi, Malcolm, Lauren, and Osco. This is an honors chemistry class. We're recording everything that's going on so you guys don't miss anything because honors chemistry is pretty tough. You need to not memorize, but learn and understand everything that is taught.
All right, so we're going to get right to the learning part of this. Yes, everybody else says hi as well. All right, if you remember yesterday, we left off with these structures are up here on the board. Now, the whole idea, and maybe we back up. Let's first do a little story. Two atoms walk into a bar. All right?
And one atom says to the other atom, talking atom.
No, not quite, Tess. So what are those two atoms going to talk about first?
Oh, electrons. They're going to give me electrons.
They're going to talk about their electrons, right? Sure. So the two atoms, and so what type of atoms could we be dealing with?
Metals and non-metals.
Okay. Well, atoms that want to gain electrons, and elements that want to lose electrons, or that would prefer to lose. So if you have an atom that wants to gain and an atom wants to lose, then what happens? One that wants to gain and one that wants to lose,
Ionic. We're going to react.
they would transfer the electron, right? So the electron would transfer. One would say, oh, okay, here, you can have my very few valence electrons and add them to your rather full shell of valence electrons. And then the two of us combined, each of us would then have a stable configuration, that noble gas configuration on the outside, right? Okay, so that's one option. What's another option?
Two non-metals.
Right, two atoms that both need to gain electrons to become more stable. So in which case then they end up, they share electrons so that both of them feel like they have 8 electrons around them. All right. Okay, now remember that it's not quite that simple. If we go back to this picture here, we see that we recall that it's not just transferring versus sharing, that there's a whole spectrum in between. So at one end, we have our hydrogen, the H2, where the difference in electronegativity, the difference in the pull is 0. Right? And over on the other extreme, we have a difference in electronegativity of 3.3, so that would represent the total transferring. But then we have this kind of imaginary line in the middle, right, the 1.7. So if the difference is less than 1.7, but greater than about 0.3, then you would have what's called a polar covalent bond. Right? And these kind of bonds are going to be very interesting to us. So we want to be able to identify those. So that's what last night's homework was about, was looking at different types of covalent bonds, right, and identifying where they might fall in this range, which ones are more, which bonds are more polar than others, that kind of thing. So let's take a minute to look at the homework then. Were there any of those that that gave you particular issues? All right, first Quan.
23.
I don't know what it was. You have to tell me.
It was like which atom has the negative of any given compound. It was
Oh.
HCl, and it was like which one.
Right. So how do you tell?
I just said the second one.
Okay. Well, you're always going to look at the electronegativity. Which one's got a greater pull? Right. Now, if you have a chart of electronegativities, then you can look on that, but then that's not really much of a challenge. It's more challenging if you have to do it based on the periodic table. So, for instance, if you had HCl, hydrogen's way over on the left, but it's up at the top. So remember, a top on the left is decent electronegativity. Bottom on the left is really low. And then we've got chlorine over here on the right. So chlorine is all the way over to the right, basically, and it's pretty high up. So it would have a pretty high electronegativity. So you'd expect chlorine to have the higher electronegativity. So if you were going to draw that, we would say HCl, and we would have an arrow pointing toward the chlorine. Now we're going to take a look at what this kind of means. This one hydrogen how many protons are in that hydrogen? Yeah, just one proton. Okay. And in the chlorine, how many protons are there? 17. Okay. Now, if we kind of forget about the bonding that might happen here, the sharing, how many electrons are around chlorine? 17? And how many electrons are around the hydrogen? All right. So in general, if we look around the hydrogen, it's basically balanced in charge. Right? There's no net charge there. Look around the chlorine, it's pretty balanced. Right? Now, what we're going to do is we're going to take that one electron from the hydrogen, and we'll take one of the electrons from the chlorine, and we're going to put them between them. Right? Now, if those two electrons are shared equally, right, they're shared equally, then we still have a pretty balance of charge, right? Because the one of these, the electron density here will cancel out this plus, and then it'll add to the 16 electrons over here, and we'll end up with an overall kind of balance there. Okay, but the problem is, or not the problem, the reality is that chlorine has a stronger pull on those electrons, right? So instead of those electrons being right there, it's going to make me do this. Well, we're going to move those electrons a little bit closer to the chlorine. Right? So now, when we look at this, what we see is hydrogen has a little bit more positive charge. There's still some electron density around there, but there's a little bit more positive charge there than there is negative. So this end of the molecule is going to be partially positive. And then when we look over here, we see 17 positives, and then we see a little bit more than 17 electrons worth of electron density here. Right? So a little bit more. So that's going to make this side partially negative. Right? Not quite as much. I mean, obviously, if this was ionic, we would move the electrons completely over there, and then this would have a full negative charge, and the hydrogen would have a full positive charge. Okay? That good then? Can I give us a little perspective there? Okay, now going back to this picture here then, ultimately this is where we want to get to. In the water, the bonds between the hydrogen and the oxygen are polar bonds, right? Difference of 1.1. In the carbon dioxide, again polar, difference of a little bit less, 0.7. So both of these have polar covalent bonds. Right? But this molecule overall is going to have a negative side to it and a positive side. Whereas carbon dioxide will have some negative buildup over here and negative buildup over here, but it's not going to be, overall it's not going to be a polar molecule.
How do you tell that?
Well, look at it. If I pull electron density this way and this way, what happens up here? More negative. So if this end's more negative, this end has to be more positive. Now I look at this one. I pull electrons this way and I pull electron density this way. Does one side of the molecule become negative? No. So this would not be a polar molecule. Right? Now, what do we know about carbon dioxide and water? Huh? They're both gases?
No, water is a
Yeah, they're both covalent. Huh?
Water can be found in multiple. They both
Their
contain.
need is for life.
No, look, simple. Think really, really simple.
They both have oxygen.
How do we usually find water?
Liquid.
As a liquid. Yeah. How do we usually find carbon dioxide? As a gas. Why do you think that's so? Why would those molecules come together to make a liquid for water, but they just fly wherever they want to for carbon dioxide?
Because
Because when liquids they're attracted to other molecules.
Yeah, the attractive forces. Right? Remember we studied solid, liquid, and gases. The attractive forces are stronger. Right? So yeah, the reason water is a liquid is because the attractive forces are stronger in water than they are in carbon dioxide. Because of this thing that's happening here. Right? So we need to understand this stuff in order to start, looking a little bit more closely at the properties that we observe. Now, the question though is, why is, because there's polar bonds in both of these. Why is water a polar molecule and carbon dioxide is nonpolar? The shape. Excellent. Did you say that? Zoe said that. Yeah, it's the shape, right? If water looked like this, if water looked like that, would it be polar? No, because all of the electrons would get piled up in the middle of the molecule, not on one end, not on one side, but in the middle. So that wouldn't be polar. Water would be a gas at room temperature and pressure. We wouldn't exist.
So polar are liquid.
Well, no. Not always. Okay. It depends on other. The other things contribute to the attractive forces other than just polarity of the molecules. Right. The size of the molecule is important too. Right. So, but we'll get to that. But the point is that to really interpret this, we need to know the structure of molecules. So that's where we're headed. Right. So in the next week, next week or week and a half, you guys are going to be able to figure out the structures for all different molecules. Right. Now, the first step in that is doing dot structures. Actually, I'll give this to you in just a minute. All right, these are called Lewis dot structures. For ionic substances, these are going to be pretty simple. We're just going to show an example of this and then move on from it because they're pretty boring. If I take sodium and chlorine, and these dots that I'm going to use are going to represent valence electrons. Right, so remember in the last chapter when we talked about you have to figure out how many valence electrons there are really fast. Right, this is where that's going to pay off. Right. So how many dots am I going to put around sodium?
One.
Good. One dot. And how many dots am I going to put around chlorine?
7.
Very good. Okay. Now, I'm usually going to put these in pairs. All right, so you're going to find those in pairs. They're not just kind of randomly thrown around there. But notice that I'm not really concerned about which ones are s electrons and which ones are p electrons. They're just going to be put around there. Okay. All right, now, what type of elements do we have? Sodium?
Metal.
Chlorine? Nonmetal? Right, so we're going to imagine the transfer of the electrons here. And we'll end up with sodium plus and chloride minus. And voila, that would be our dot structure showing what happens when a metal and a nonmetal come together to make an ionic compound. And of course, if you did magnesium, magnesium would give away 2 electrons, so you might have magnesium 2 chlorines. And 1 electron would go to each chlorine.
You just draw like a little
Maybe. I might be tempted to just draw 2 chlorines,
Okay.
just to show my in-depth knowledge and non-laziness. All right, now, so the covalent ones are the ones we're going to be spending most of our time with. All right, so let's take a look at hydrogen, and we'll do chlorine again. We already know chlorine has 7 valence electrons. How many electrons does hydrogen have? 1. Right. Now the non-chemistry person would look at this and say, oh, this is just the same as the other one, right? Oh, Bianca's shaking her head. Why not, Bianca?
Okay, well,
your face when you said it. And second of all, it's because of the charges that you put there with the 2 pluses and then the minus near the.
I didn't really put any charges down for the H and the Cl. Yeah.
They're both non-metals.
Okay, they're both nonmetals. But hydrogen's over there with the metals, isn't it?
Hydrogen
No,
only
but
has
it's
one
like on the
electron.
periodic table that's right there, the one that you give us for tests, it's like kind of in the middle. Like, you know
If
how
it
it's
loses
You know
an
that
electron,
project
it's
we
no
did
electron.
with
If it loses
the
that
man,
electron, it
and
doesn't
they
have
had
any
both
more.
properties over here or there?
Mm-hmm.
You know that project we did with the people?
yeah.
Right.
And the first person that on here could have gone here.
Right.
Or here.
Yep, good. Yeah, Tessa's talking about the SPIES right now, the SPIES mission. Yeah, think about it. With sodium, sodium's only option is to give up its 1 electron, to have a full valence shell. Hydrogen, on the other hand, only needs 1 to fill up its valence shell, because it only has a 1s. So for hydrogen, it only needs 1 more to fill up its valence shell, so that's very much like the halogens. They only need 1 more. So what's going to happen then is each of these will contribute 1 electron to make the other one happy. And so we get that kind of a structure there. When we look at each of these, we should be able to draw circles around each element and show that each one has the number of valence electrons that they're looking for. Again, remember, hydrogen only needs 2, because it only has to fill up that 1s orbital.
Like a Venn diagram.
Right.
Or maybe one of those.
Okay. So we're going to pause just for a second.
Hey,